to Introduction to Aerodynamic Objects tutorial for Weathervane. And in this tutorial we're going to make something that moves due to aerodynamic forces and understand what it means to be aerodynamically stable. What we're going to do is make a vertical fin and then verify that lift behaves in the expected way as we vary the wind direction. And then we're going to turn that fin into a weather vane by attaching it to a rod that can rotate around a pivot point. And we're going to vary the wind direction and see that the weather vane points into the wind. Then finally we're going to add a horizontal tail so that it can respond to both changes in wind azimuth and wind elevation. This is our scene diagram. So we're going to be building something like this. We have got a rod with a pivot point, and then we've got a vertical stabilizer and a horizontal stabilizer here. And from previous tutorials we've made an aerodynamic object. The difference here is we've now got two aerodynamic objects and they're sharing the same rigid body. So here we are in Unity. I've already got a uniform flow component and some flow field arrows, so we can get straight on and build our vertical stabilizer. So I'm going to do right click, create empty, call this vertical stabilizer. And we're going to put a rigid body at the top of this, at least for now, to test it. And we're going to fix this in space because to start off with, we just want to verify that our forces are doing what they should do. And as in previous tutorials, we're going to do the same process for building things up. So we're going to add some geometry in. We're starting with a cube, but this time we're building a vertical wing as opposed to a horizontal, and Aerodynamic Objects doesn't mind about that, but this is for us to make sure we do things the right way around. And we're going to make it 3 centimeters thick, 2 meters tall, and 0.7 meters chord. Okay, next let's add the aerodynamics. So I'm going to do create empty, and then we're going to add our aero object component, and we want drag and lift. We need to connect up our rigid body, and since this is a rectangular planform, let's just use the rectangular reference area. Okay, so that would produce aerodynamic forces, but we won't better see what's going on, so let's add some visualization components. So let's do a wind arrow, a drag arrow, and a lift arrow. Excellent. I've got my uniform flow set up on a locked inspector tab here so I can see what's going on. I'm going to hit play, and now if we increase the wind speed, we can see we've got some wind on our vertical stabilizer, but nothing is happening because it's a zero angle of attack. But if we vary the wind azimuth, you can see we're generating lift. And if we look at it from top down and do the same thing as we vary the wind azimuth, you can see as the wind comes from one side we get lift that way, wind comes from the other side. And so that's acting as a fin. So depending on which way the wind's coming from, that fin is going to be pushing back in the other direction. Next up, let's build a rod which we can attach this fin to turn this into some sort of weather vane. Okay, so let's create a rod, and a little bit like building an aerodynamic object, we're going to do the similar thing. At the top level we're going to have a rigid body, and on this one I'm going to turn off the angular drag. And what we want now is to constrain this, so I'm going to fix it in space. And I'm also going to allow it to rotate around the y-axis. So I'm going to fix off those two and leave it free to rotate in y. Let's add some graphics onto that. So 3D object cube. So this is our geometry. And what we're going to have is a rod that is 15 centimeters by 15 centimeters. So 0.15 by 0.15. And it's going to be 5 meters long. And if we were building an aerodynamic object, so if we wanted actually to get aerodynamic forces on this rod, the next step down would be that we'd create another child object with aerodynamics on. But actually, in terms of our modelling strategy, most of the aerodynamic forces is going to be coming from the fin itself, or the stabilizer. So to a first approximation, we can ignore the aerodynamics of the rod. It's there for our geometry and inertia, but it's not there for the aerodynamics. So we're not going to put any aerodynamic model on that rod. Let's have a go at attaching the fin to that. So what we're going to do is grab the fin and move it back. And at this point, we could, we've got a rigid body on both of these objects, we could put a joint between these two and connect them together. But at the moment, they're just in the same place as space, but they're not actually connected. And just to verify that, if we take our rod and if I spin it around the y-axis, the rod moves independently to the fin, because they're in no way connected. They're not connected via a joint, and they're not connected via the hierarchy. So what we need to do is make the stabilizer a child of the rod. So I'm going to grab the vertical stabilizer and drop it onto the rod. So now if I move the rod, this is basic kind of working within Unity's scene hierarchy, but there it's moving together. But I have a rigid body both on my vertical stabilizer and on the rod. But the simplest modelling approach here is just to have one rigid body and then use the aerodynamic forces from all the different components and apply it to the same rigid body. So what I'm going to do is delete this rigid body from the fin, and we are going to use the rigid body of the rod as the point where we apply the forces. So if we go down to the aerodynamics of the fin, it'll say missing because we just deleted it. So I'm now going to apply the rigid body from the rod. The other thing, as a bit of a subtle point, but in terms of where you get your velocities from, if you remember before, we got the velocity from the rigid body. And we kind of could do that in the sense of the rigid body of the rod is in the middle. The kind of wind there is pretty similar to what's going on at where the stabilizer is, but actually it's out there in a different place of the flow field and it's moving in a different way. So to make this a more realistic model, we'll use the transform position to get the velocities. So on here we have body velocity source, and by default it's the rigid body, but we can change it to transform. And what that means is that it will use the transform velocity to get its body velocity rather than the velocity of the rigid body to which it's sending its forces. Because we're human beings, it's nice to see what's going on properly, and actually what I'm going to do is create a bearing for this thing to rotate round, and this really helps us orientate. So I've just made a little round sphere. It does absolutely nothing apart from just gives us kind of a visual anchor, and I'm going to make it a child of the rod, and that's at 0, 0, 0, and what we want is the rod to rotate around that point. And if we go up to the rods here, some of the settings we haven't looked at before, but if you're on your rigid body, you've got your center of mass, and by default it's automatic. Collect up all the child colliders on its object and works out the centre of gravity from that. And if we let it do it automatically, the centre of gravity would come out somewhere towards the back because we've got a fin on. What we want is the centre of gravity to be precisely at 0. And so what we're going to do is uncheck automatic centre of mass. And then, yeah, by default there it's gone to 0, 0, 0. So that means our centre of mass is going to be there. Okay, and our constraints are about centre of mass, so we're constrained about x, y, and z. It's going to be fixed there, and it's going to rotate around the y, the green axis. Okay, so let's just quickly check what we've done. We have got our rod top level object with a rigid body on it, free to rotate in y. We've got some geometry for the rod. And now we've got our vertical stabilizer model, so we've got some geometry for that, and then we've got our aerodynamics applied to this vertical stabilizing surface there. Okay, let's see what happens. So first off, nothing happens. That's fine. But if we now change the azimuth of the wind, we've made ourselves a weather vane. So if you look there now, the weather vane points into whichever direction the wind is coming from. As you can see, as the wind changes, the aerodynamic forces on that fin are forcing the rod to spin until it lines up with the wind, and then those forces go to zero when it's lined, and then it stabilizes in that direction. So what that means is that weather vane is a stable system in the sense it always moves such it's pointing into the wind. And if we add some turbulence onto that, it's going to be sort of knocked around a bit, but it's always going to be trying to point roughly into the wind on average. And just while we're here, I talked about changing the velocity source for the aero objects. It's all moving rather quickly, but the blue arrow here is the velocity sensed at where the fin is, and the blue arrow here is the velocity sensed where the rigid body is. So actually under this setup with lots of turbulence, it's actually quite important that you change the reference point to where you're getting your velocities from to the transform. So that's a weather vane, and really all a weather vane is, it's just a wing on a stick, and that wing has a force on it, and it moves the stick until the forces go to zero. Okay, that's working just in the azimuth direction, but why not make a weather vane that points in any direction? So if the wind's coming up or down, can we make it so it points into that? So it's kind of universally stable, that it always points into the wind. And the answer is yes, of course we can, and we're going to do that by putting a horizontal stabilizer in the other plane, so that now if we get a wind velocity coming from up underneath, it should push the nose down, and vice versa. If the wind comes from the top, it should lift the nose up. So let's do that, and because we're lazy and smart, we're going to do it the lazy smart way. So instead of building a whole new wing, we're just going to duplicate the existing vertical stabilizer, rotate that around the Z axis. So just type 90 in there, spins it round, and there we go. We've made a fully functional horizontal stabilizer with almost no effort. There's actually nothing else we need to do apart from just rename it for the humans, and we need to release this joint now so it can rotate in pitch as well. So if I go up to the rigid body there, I need to release it in the X direction as well. Okay, as ever, nothing happens because we're exactly lined up with the wind. But now if we change the elevation, the wind's now blowing straight down, and our weather vane is pointing into the wind. And we can do any combination of pitch or yaw, and the weather vane will point into the wind. Okay, then to summarize what we've done, we built ourselves a weather vane, and we did that from two separate aerodynamic objects. We built our vertical stabilizer, and then we duplicated it and rotated it 90 degrees, and that's got our horizontal stabilizer. But the difference between these objects and the ones we made in the previous tutorial is that they now share a common rigid body, which is not placed on each of the objects. And this rigid body is on the rod of the weather vane, and these guys here are children of that, so the whole object moves together. We've seen this concept of aerodynamic stability, so by putting these stabilizing surfaces on the back of a weather vane, we can make it so this thing always points itself into the wind. Great, so that's the end of this tutorial. In the next tutorial, we are going to be putting a wing on this object, so you can see where it's going. We're building out the capability to make something that is not only stable, but produces lift, and then we can start producing objects that really fly.